Welcome to the second part of sixth lecture. So, in the first part we talked about one lemma that suppose S is a subset of the vertex set V and S complement is V minus S, and let E be the minimum cost edge. Connecting S complement means is a minimum cost edge of the cut S complement, then E must be part of minimum spanning tree. Okay, so this is important result, and this sort of signify why Prim's algorithm is correct. Suppose we have minimum spanning tree T not containing E. Then we prove that T is not a minimum spanning tree. Okay. So, let this edge minimum cost edge connecting S and S complement, this edge be U V, and this is the minimum cost edge connecting S complement. So, suppose this is my S, this part is S and this part is S complement, and this is U and this is V. So, this is E. Okay. So, where U belongs to S and V belongs to S complement. Now, since T is a spanning tree, let me draw a spanning tree, this is a spanning tree, for example, just to explain okay. So, this red tree is the spanning tree, suppose. Well, then since T is a spanning tree, U and V must be part of this tree, right, because it contains all the vertices. It contains an unique path from U to V, which together with U V together with E, which is U V, forms a cycle. See, the red thing is the spanning tree, and since it is a spanning tree, it includes all the vertices. So, it includes U and V also. Now, in a tree between every pair of vertices, say u v, there is a unique path. So, this is the unique path from u to v, and now E is not part of this tree. So, along with this E it forms a cycle. So, this is what this line says. So, this path, so I am talking about the path, this one, the path which is from u to v, this path, this is the path, unique path from u to v in the spanning tree T. So, I am talking about this path, means this green path. This path has to include another edge f connecting S and S complement. This is true because at this, at least for this example, you can see that this part includes another edge, that edge, the edge f is this one. This is the edge I am talking about. So, this is the edge which is connecting S and S complement, and this edge is there in the minimum spanning tree or in this green path. So, this is what the f is. Okay. Now, we will form another tree which has cost less than t. That tree is t plus, now I will include E in the spanning tree and remove f, t plus E minus f is another spanning tree and has less cost than t, right, because now what I am doing is that I started with this red tree, and then I know that this is also edge connecting S S complement, but among all the edges which are connecting S S complement, E is the minimum cost. Now, what I do is that I remove this edge from this red tree, and then I include this edge in the red spanning tree. Instead of f, remove f and add E, and this tree has less cost because the cost of E is less than or equal to the cost of f, because E is the minimum cost edge connecting S and S complement. So, we got another spanning tree which has less cost than t. So, we proved that t is not minimum spanning tree. Okay. This is what we wanted to prove. Now, the significance of this is that you can see that in the previous algorithm, every time so this algorithm gives a way of defining S. So, S is the tree edges at any stage, and S complement of course V minus S, and what this nearest neighbor operation, what it does is that it just identify the minimum cost edge between S and S complement of this cut, and that edge is included in the set of tree edges. So, this is how this Prim's algorithm sort of ensured that at every step whatever partition you have, the partition you get from the previous or existing tree, and you at the next step you include an edge which is the minimum cost edge in the cart S complement or minimum cost edge connecting S and S complement. Okay. So, this is what all that is what I wanted to say about Prim's algorithm. Next, we move to the matching in a graph. So, we learn what is matching, and we spent significant amount of time in matching. So, first today we will talk about how to find maximum matching in bipartite graph using augmenting path algorithm. So, let us start with matching. Okay. So, informally speaking, matching in a graph is a collection of disjoint edges or independent edges, sometime we call. Let me give the formal definition. A matching M in G, the graph G, is a set of edges such that every vertex of G is incident to at most one edge in M. Let me explain because the definition should be very clear what is matching in a graph. Let me start with the bipartite graph. And for the practical point of view, I consider this example. Suppose there are 4 girls. So, there are 4 girls, call them G 1, G 2, G 3, G 4, and there are 5 boys, and call them B 1, B 2, B 3, B 4, B 5. Now, I construct a bipartite graph. On the left part, I have all the girls, 4 girls. So, G 1, G 2, G 3, G 4, and on the right part, because bipartite graphs, we partition the vertices into 2 parts. You have B 1, B 2, B 3, B 4, B 5, and there will be an edge between B I and B j if they are friend to each other or they like each other. So, G 1 B 1, that means the girl G 1 likes boy B 1, and similarly the girl G 1 also prefers B 4 and B 5. Girl G 2 prefers only B 1, girls G 3 girl G 3 prefers B 2, B 3 and B 4, and G4 prefers B2 and B4. Now, what is a matching? So, matching means it's a matching just, I mean you can't match one girl with two boys. So, one girl will be matched with one boy. Similarly, you can't match two girls with one boy. So, that is why this is that it is a collection of edges such that every vertex of G is incident to at most one edge in M. So, let me give one example of a matching here. One matching could be G1 B4, G1 B4. So, G1 is matched with boy 4 and G2 is matched with boy 1 and G3 is matched with boy 3 and G4 is matched with boy 4. So, here this is the matching. So, matching here the M, the matching that I talked about is consist of 4 edges, that is see you can't match G1 with B2 because G1 does not prefer B2. So, you have to choose find out a subset of these edges. You can't just arbitrarily assign G1 or match G1 with B2. So, the matching M here is G1 B4. I am just omitting the comma here. G2 B1, G3 B3 and G4 B2. So, this is a matching and it satisfies the property of the matching that every vertex, now you can see that every vertex is incident to at most one edge. So, this one edge in M. So, these are the edges in M. Now, we can see that B is incident to only this edge, B2 is incident to only this edge. I am talking about the red edges only. B3 is incident to this edge, B4 is incident to this edge, B5 is not incident to any matched edge. So, here B5 is actually unmatched, it left unmatched. All the girls are matched. Of course, there are 4 girls, you can match with 4 boys only. So, one boy extra is the B4, we call B4 is not matched. And the red edges are called the matching edges and the other edges are called non-matching edges. So, these are the matching edges. Okay. So, the size of this matching, the size of a matching is the number of edges in the matching. So, the size of this matching is equal to 4. So, formally the size of a matching is the number of edges in that matching okay. And a matching is maximum or a matching is a maximum matching when it has the largest possible size. Yes. So, here it is not difficult to realize that this is a maximum matching, because you can't include another edge. So, all the girls are matched. So, you can't include another edge. Of course, this is also a matching. If I say m naught is just for example, just G1 B4, this is also a matching, but this is not a maximum matching, whereas this is a maximum matching. Okay. So, the optimization problem here to find maximum matching, because finding minimum matching is a trivial problem, and a perfect matching in a graph is a matching that matches every vertex. Right. So, this is not a perfect matching, because not every vertex is matched here, B5 is not matched. So, this is not a perfect matching, but this is a maximum matching. Also, it is not difficult to realize that in order to get perfect matching, the number of vertices in the graph must be even. So, here the number of vertices is 4 plus 5, 9. So, it is an odd number. So, you will never get a perfect matching, it is very obvious. So, we have a maximum matching here, but not perfect matching. Okay. So, if perfect matching does not exist, we are interested to find a maximum matching. Obviously. So, here the optimization problem is to find, given a bipartite graph or any general graph, yeah, slowly we will learn, the problem is to find maximum matching. Okay. Next, we learn few definitions. One is called alternating path and augmenting path. So, let M be an arbitrary matching. So, we can think of say start with any matching, and the question here is that if M is not maximum, how could we improve it? You start from arbitrary matching, the ultimate goal is to find maximum matching. You start from an arbitrary matching and then you improve it to get a maximum matching. Okay. Next, we talk about two definitions. One is called alternating path, and alternating path is a path that alternate between matched and unmatched edges. Unmatched edges. Okay, so I can probably give an example here. This is an alternating path. So, B5 to G1, sorry, B5 to G1, this is a unmatched edge, and then from G1 to B4 this is a matched edge, and then B1, sorry, B4 to G1, B4 to G3. So, this is unmatched, this is matched, this is unmatched. So, this is a alternating path from B5 to G3. Yep. And an augmenting path sorry about this, an augmenting path is an alternating path that starts and ends on unmatched vertices. Okay, so, this is what the definition of alternating path, which is very important. I can't give an example of alternating path at this moment, because this there is no alternating path probably with respect to this matching. So, this path is an alternating path, but this is not an augmenting path, because the augmenting path should start with the unmatched vertex and also end at the unmatched vertex, but G3 is not an unmatched vertex, it is a matched vertex. So, this is an alternating path, but this is not an augmenting path. Maybe in the next lecture we talk about augmenting path in details, and we give an augmenting path algorithm to find maximum matching in a bipartite graph. So, the augmenting path algorithm starts with an arbitrary matching or even a null matching. There is no edge in the matching at the beginning, and then at every step it will find an augmenting path with respect to the current matching and improve the matching size by 1 at each step, and the algorithm will stop when there is no augmenting path with respect to a given matching. So, augmenting path, alternating path, everything is with respect to a given matching, because it is the edges alternate between matching and unmatching edges. Okay, so, we will learn about augmenting path algorithm to find maximum matching in bipartite graph in the next lecture. Thank you very much.